Hello everyone, welcome to my second video on theory of groups. In the previous video, we have discussed about the definition and properties of groups and subgroups, and at the end we have proved two important theorems on groups. In this session, we shall continue the proof of a couple of theorems on subgroups. So let us consider the first theorem of this session. Here it is given that H and K are two subsets of a group G. So G is a group, H and K are any two subsets of a group G. The theorem is to prove that HK, that is the product of H and K, is a subgroup of the group G if and only if. So again we have to prove the theorem in two directions, that is if HK is a subgroup, then HK is equal to KH. Conversely, if KH is equal to HK, that should imply that HK is a subgroup. So this theorem we have to prove now. Let us begin the proof. First, suppose that, as I have already told you, whenever if and only if type of theorems are to be proved, that is this type of theorems are to be proved, we have to consider in the first phase the necessary condition. So what is the necessary condition? KH equal to HK or HK equal to KH. First suppose that HK equal to KH. What is now to be proved? We have to prove that HK is a subgroup of G. So in order to prove that HK is a subgroup of G, we have to use the previous theorems, one of the previous theorems, either the first theorem or the second theorem. Here we have used the second theorem. So condition for any subset H to be the subgroup of the group G is that for any two elements of that particular set, we should have the binary composition of the two elements AB, that should be in H, and inverse of any one of those two elements, that is A inverse or B inverse, that should be present in H. So this was the statement of the second theorem. This should be true. So we have to prove this particular result here. Now again, one more thing we have to keep in our mind, that what actually this KH stands for. See, KH or HK, we shall take first HK. So HK is a subset of G which contains the elements like small h into small k. Here into means whatever is the binary combination defined, binary operation defined in G, that particular operation. So H star K you can say. In order to have the convenience, we ignore star and we simply write HK, as I have told you in the previous lecture. So HK is a subset which contains elements like small h, small k, such that this small h belongs to the first set, that is capital H, and this K belongs to the second set, capital K. It belongs to the second set, capital K. So if this is the so HK is a set containing this type of elements. Okay, HK into KH, where HK is, where H is the member of first set and K is the member of second set, capital K. So similarly KH means it is the set containing the elements like small k, small h, where small k belongs to this capital K and the small h belongs to this capital H. So in this way we define the two sets KH and HK. Now what we have to prove? We have to prove that this HK is a subgroup. To prove that HK is a subgroup, take any element X belonging to HK. As per our definition of HK, every element of HK must be in the form small h, small k. Therefore, X must be in the form small h, small k, where small h belongs to capital H, small k belongs to capital K, as per this definition I have just now told you. Similarly, you take another element Y belonging to same same HK, the same set HK. Now, Y should also be in the form H dash K dash. So, other than HK, we have to take two elements, namely H dash belonging to capital H, K dash belonging to capital K. So, this every element of HK must be in the form of the product of HK or H dash K dash. So for X we have assumed HK, for Y we have assumed H dash K dash. Now consider XY, the product of just like AB. We have just now taken for every A comma B, what should we have? The first condition is that AB must be in H. For it is the previous theorem which we have taken in the last class. So for any two elements AB belonging to H, A into B must be in H and A inverse must also be in H. So this type of result we are now trying to establish. So here we are considering XY. So what is this XY standing for? X, the value of X is small h, small k. Y value is small h dash, small k dash, according to this. Now, associativity property holds in G, therefore we can take a bracket for these two. So we have kept the first and last element outside the bracket, and within the bracket we have taken the middle two elements HK, this product KH dash, we have taken this product. Now, see KH dash, what type of element KH dash is? KH dash is the element with K in the beginning, therefore it should be in capital K. This K is in capital K, H dash is in capital H. Therefore this product KH dash must be in capital K, capital H. And we have already assumed in the beginning itself this particular thing, that is KH is same as HK. Therefore, here we have written it KH is equal to HK. Now what we have in our hand? In our hand we have this particular HK is same as KH. Because of that, this element which was the member of KH is also a member of HK. So therefore it should be of the form, when HK dash is in capital H, capital K, it should be of the form sum H2 K2, for sum H2 belonging to capital H, K2 belonging to capital K. So we have proved that this KH dash is of the form H2 K2. Now let us substitute its value in the equation 1. In the previous slide we have taken the last equation as equation number 1. XY equal to this thing. Here we substitute the value of this particular quantity. So after substituting that, what we are having? We are having here H2 taken in one bracket for the sake of our convenience, K2 and K dash taken in the second bracket. So as per the associativity property, we can interchange the brackets. So we have this particular thing, H2 K2 K dash, and obviously H into H2 is some element like H3, K2 into K dash. K2 is a member of K. K dash is a member of K. Therefore, K2 into K dash, according to closure property, this is an element of capital K. Let us take it as K3. Now, the element of H3, sorry, element of capital H multiplied by element of capital K, definitely it should be in the set capital H into capital K. That is what we have written here. So this product belongs to HK. So what we have proved, the product XY is belonging to capital H into K. So for any two elements XY belonging to capital HK, their combination, their product is also a member of HK. Thus HK is satisfying the closure law under the binary operation of multiplication. Now consider this definition. Now I have shown you in the previous slide here. See, for any two elements, this must be proved. The first condition must be proved and the second condition must also be proved. We have now proved the first one. Let us go for the second one. So A inverse should also be in that particular set. Now consider inverse of X. So inverse of X value is H into K. So according to reversal law of inverses, what we have in reversal law of inverses, AB whole inverse is B inverse A inverse. Therefore it should be K inverse H inverse. So K inverse is an element of K, H inverse is an element of H. Therefore K inverse H inverse must be an element of K into H. But our assumption is that KH is equal to HK. Therefore K inverse H inverse must be in HK, or its value, it is the value of X inverse. Therefore X inverse must be in HK. So that is what we are having here. X inverse is in HK. So the second condition, what we were intending to prove, that we have proved. That is, this as well we have proved. Now let us go for the conclusion. So because of XY belonging to HK and X inverse belonging to H, we can say that HK is a subgroup according to theorem number 2. So this completes the first part, that is direct part of the proof. Conversely, suppose that HK is a subgroup and now we have to establish the result HK equal to KH. So as I have told you already, whenever we want to show that a set A is equal to another set B, what we have to prove? We have to prove that A is subset of B and B is subset of A. So this is the most important result of set theory. This we have to establish now. So HK must be a subset of KH. KH must be a subset of HK. This we have to establish. First let us establish this thing, that is KH is subset of HK. So how to prove that? How to prove that KH is a subset of HK? To prove that any set A is a subset of B, you take any arbitrary element of A and do some work. At the end you prove that that element is an element of B. Then we can say that A is subset of B. Similarly, to prove that KH is a subset of HK, take an element of KH. What type of elements will be there in KH? The elements of the form small k into small h. Small k belongs to capital K, small h belongs to capital H. See, the element small k into small h is an arbitrary chosen element of capital H, capital K. Now, we have already considered that HK is a subgroup. When HK is a subgroup and we are having the element here K belonging to capital K, small k is an element of capital K, small h is an element of capital H. Therefore, according to the definition of subgroup, it should be a group. Therefore, H inverse must be an element of capital H and K inverse must be an element of capital K. So we are having two elements H inverse, K inverse respectively in the sets capital H and capital K. Therefore their composition, their product H inverse, K inverse must be in the set HK. Right? Now HK is a subgroup. We have taken here HK is a subgroup. We have already taken that HK is a subgroup. Therefore, inverse of every element exists. Inverse of this element exists in HK. Therefore, inverse of this element, whatever we have shown here, that should also be in HK. Now, according to the reversal law of inverses, inverse of this into inverse of this. So that is what we have taken here. Now, that should be in HK. RHS is being kept as it is. We are simplifying the only left hand side. Now, K inverse whole inverse is K. H inverse whole inverse is H. So what we have proved? KH is belonging to capital HK. Initially, we took KH as an arbitrary element of capital K, capital H. And we have now proved that KH is also an element of HK. So therefore, every element of KH is an element of HK. Every element of KH is an element of HK. Therefore, HK is subset of KH is subset of HK. So the first part we have proved. Next, to prove that we are intending to prove this thing. That is, HK is a subset of KH, that we want to prove. To prove that HK is a subset of KH, take any arbitrary element of HK. So take X as an arbitrary element of HK. HK is a subgroup. We have already assumed in the beginning of the converse part of the proof. So when HK is a subgroup, it must be a group. Therefore, inverse of every element should exist. Therefore, inverse of X must exist in it. Therefore, X inverse belongs to HK. When X inverse belongs to HK, X inverse must be of the form HK. See, X inverse is an element of capital H, capital K. In capital H, capital K, what type of elements are there? Small h into small k type of elements are there. Where small h is belonging to the first set, small k is belonging to the second set, capital K. So therefore, this X inverse must be of this kind. Now you take inverse of this X inverse. So X inverse whole inverse equal to inverse on the right hand side. Now let us simplify. X inverse whole inverse is X. This is very, very simple. Now the reversal law is applicable here. So it is K inverse H inverse. K inverse H inverse, of course, it is an element of KH because K inverse belongs to capital K, H inverse belongs to capital H, K inverse into H inverse belongs to capital K into capital H. So what we have proved? X is belonging to capital K, capital H. We have proved this. See, we have started with our assumption that X is an arbitrary element of HK, and we have proved that X is also an element of KH. So we can say that every element of HK is an element of KH. Therefore, HK must be a subset of KH. So what we have proved? We have proved that in equation number 4, we have proved KH is subset of HK. And now we have proved that HK is subset of KH. Therefore, we can conclude that HK is equal to KH. So we proved the theorem. What we proved? We proved that HK is a subgroup if and only if this condition is satisfied. So now let us move on to the next theorem. Again, G is a group with the binary operation star, or it can be taken as multiplication. H is any subset of G. It is a subgroup. H can be taken as a subgroup of G if and only if the product H into its inverse, H inverse, is equal to H. You should understand again what is H inverse. H inverse is the set containing, see, H inverse we are speaking about. H inverse is the set containing the elements like small h inverse, where this h is a member of capital H. See, capital H inverse is the set of all the inverse elements of capital H. Take any element of capital H, take any element small h belonging to capital H, and its inverse will be there in capital H inverse. Now, H inverse means, so H inverse is the set containing the elements like, see, an element of H may be H1 and an element from capital H, H inverse. H inverse means it may be H2 inverse. See, you don't consider H1 into H1 inverse, because it is identically E, it becomes identity element. So apart from that, you consider any general element H2 inverse belonging to capital H inverse. So H inverse is the set containing the elements like H1 into H2 inverse, where H1 is element of capital H and H2 inverse is an element of capital H inverse. So this is the thing here. Now, first suppose that this condition is this condition. So H inverse is equal to H is valid. Now to show that capital H is a subgroup, we want to show that H is a subgroup. To show that H is a subgroup, you take any two arbitrary elements of H. Take any two arbitrary elements of H. And when B belongs to H, B inverse should also belong. See, when B belongs to H, as per this definition, which I have just now given you, B inverse must be an element of H inverse set. See the set H inverse. H inverse is containing all the inverse elements of capital H. So when B is an arbitrary element of capital H, its inverse will be there in H inverse as per the definition given here. Now we are having the element A. We have just now said that A is an arbitrary element of H. So that is what we are taking. A is an element of H, and as per this, B inverse is an element of H inverse. So what we are having, AB inverse. AB inverse must be, it is a product, it must be in the product set, that is H inverse. So AB inverse is in the product set H inverse as per this definition which I have given just now to you. Now H inverse is equal to what? H inverse is equal to H as per equation number 1. So replace this H inverse by H on the right hand side, left hand side AB inverse kept as it is. So what we have proved, for any two elements AB belonging to H, AB inverse belongs to capital S. Therefore, as per theorem number 1, H is a subgroup of G. So the first part is very easily proved. Conversely, you consider that H is a subgroup of G. We have assumed here it is a subgroup of G. Now what we have to show? We have to show the condition H into H inverse is equal to H. Again, to show that two sets to be equal, one set is the subset of other and the other set is the subset of the first one. So we have to prove that H inverse is subset of H and H is subset of H inverse. To prove that, H inverse is subset of H, consider any arbitrary element of H inverse. So consider an arbitrary element of H inverse. What type of elements will be there in H inverse? A, B inverse type of elements will be there. I have just now told you. What type of elements will be there in H inverse? An element of H and an element of H inverse. That is B inverse is the element of H inverse. So AB inverse is an arbitrary element of H inverse. Now, as per the definition, A belongs to H. That is straightforward according to the definition just now I gave you in the previous slide. B inverse is an element of H inverse. B inverse is an element of H inverse. See, when B inverse is an element of H inverse, it implies that B must be an element of H, because H inverse contains all the inverses of H. Therefore, B inverse must be an element of the must be an inverse of the element B which is in H. So now we have two elements A and B belonging to H. Just now I told you. Now this implies that For two elements AB belonging to H, what was our assumption? AB whole inverse. AB whole inverse. See, now two elements AB belonging to H, AB inverse belongs to H or not? Because of our assumption, we have supposed that H is a subgroup. When H is a subgroup, AB inverse must be in H for AB belonging to H. So AB inverse is in H. So what we have started? We have started with AB inverse belonging to HH inverse. We proved that AB inverse is in H. So every element of HH inverse is an element of H. Therefore HH inverse is a subset of H. This is equation number 2. Again, to prove that H is a subset of, HH inverse, consider an arbitrary element A belonging to H. Now, when A belongs to H, A into some inverse element, let us take inverse of the identity element. That should be in HH inverse because A is from H, E inverse is from H inverse. So, this product A, E inverse must be in HH inverse. Because E is an identity element of H and its inverse must be in H inverse. So that is why E inverse is in product HH inverse. Now A into E inverse of identity element is the identity element itself. So inverse of E is E. A into E belongs to HH inverse. A into E is A. We all know very well. That belongs to HH inverse. So what we have proved? By choosing an element A from H arbitrarily, we proved that it is also in HH inverse. So therefore, every element of H is an element of HH inverse. Therefore, H is subset of HH inverse. So we have proved in the previous slide the reverse part. HH inverse is subset of H, and now we proved H is subset of HH inverse. Therefore, we can conclude that this thing HH inverse is subset of HH inverse is equal to H. So this proves the theorem. Now let us consider an important definition here. Integral power of an element of a group. Let us consider G to be a group with a binary operation particularly mentioned as multiplication. So it is mentioned as multiplication. Now when you take any element belonging to G, A into A, A into A into A, A into A into A into A, they should all be the elements of G as per the closure law. Now when you consider A into A into A dot 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 n times, that is of course A to the power n. We define it as A to the power n. For every element A belonging to G, we define A to the power n as A multiplied n times. So this A to the power n is now again an element of G. I told you just now because of the closure law. Therefore, this particular A to the power n is now called as the integral power of A, where n is any integer. Now this expression A to the power n is called as an integral power of an element A belonging to the group G. Now consider these important notes. See, we know that A to the power 1 is A itself. A to the power 2 is nothing but A multiplied with A twice. So similarly we can define. Now what about A to the power 0? Meaning A to the power of 0 is meaning that it is the identity element. You take any element of the group G, if it is having the power 0, then it is nothing but 1. A to the power 0 is always 1, and 1 is the identity element of multiplication, that is denoted generally by the notation E. Now, if you consider A to the power minus n, you can write it as A to the power n whole to the power minus 1 by using the laws of indices. Now, it means that inverse element of A to the power n, A to the power n whole inverse, the inverse element of A to the power n is this thing, that is A to the power of minus n. Similarly, we have another note. that is based on the properties of indices. A to the power m whole to the power n is a to the power mn. AB to the power n is a to the power n, b to the power n, if G is abelian group. So this is particularly in the case of abelian group. So we have seen the properties of indices are valid here as well. Now we have another sign convention. Instead of multiplicative group, if G is an additive group, that is binary operation is addition. In that case, instead of showing a to the power n, see, a to the power n was a multiplied n times. Now we have to here add a n times, a plus a plus a plus a dot 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 n times a is being added. Now this means a, when you add 2 times it is 2a, when you add a 3 times the answer is 3a. In general, when you add a n times it is n into a. So NA is now playing the role of a to the power n, which was the notation of integral power of an element a. Now here NA is called as, this NA is called as an integral multiple of a. Instead of integral power of an element, it is called as integral multiple of a. This is in the case of additive group. It is same as integral power of an element in the case of multiplicative group. Now another definition, order of an element. So what is meant by the order of an element? See, we have a group G and an arbitrary element a belonging to G. Now order, or it is also called as period, of an element A is the least positive integer, very important, least positive integer n, such that a to the power n is equal to e. This is very important. A to the power n is equal to e. Then we write that order of a is equal to n. Order of a is equal to n. We have already seen that a to the power of 0 is equal to e for every element. But now we are searching for a positive integer. It must be greater than 0. It must be greater than 0. We are searching that type of element. So a to the power of 0, we move for searching a number greater than 0. That is the element of the number of the form n. That must be least positive integer. If that type of number exists, then we say that order of a is n. Otherwise, we say that a is an element of infinite order or of 0 order. Now identity element. Identity element is, of course, it is an element of order 1. Why? Because e to the power 1 is equal to e. E to the power 1 is equal to e, therefore order of e is 1. Now, if there exists a positive integer m such that a to the power m is equal to e, then definitely you cannot directly say that order of a is m. It is looking like that, but there can be any other element. There can be any other element n with the property that a to the power n is equal to e. Therefore, you can now say that order of a is always less than or equal to this m if a to the power of m is equal to e. Now let us consider a simple example on the order of a group. See, order of an element of a group. G is a multiplicative group of elements, 4 elements, 1 minus 1, I minus I. So these elements are the 4th roots of unity I have told you in the previous session. Now, since 1 is the identity element under multiplication, order of 1 to the power of 1 is 1. Therefore, order of 1 is 1. Consider the second element minus 1. Consider the second element in the set, that is minus 1. So minus 1 to the power 1 is minus 1, but minus 1 to the power of 2 is plus 1. Therefore, order of minus 1 is 2. Order of minus 1 is 2. Similarly, order of I. See, I to the power 1 is I to the power of 2 is minus 1, I to the power of 3 is minus I to the power of 4 is 1. Therefore, order of I is 4. And order of minus I, you see, minus I to the power of 4 is also 1. Therefore, order of minus I is again 4. So this is how we solve the examples. There are 2 examples. You please try these 2 examples by yourself. This is one example. The proof is there. The solution is there. You can refer it. And the second one, the next example. This is the next example. You please try to solve these 2 examples by yourself. With this, I would like to stop here. We will meet very soon in the next session, which will be again on the properties of order of an element. So I thank all of you for watching my video. Thank you.